Now that we've talked about finding the probability of an event, we now go on to discussing combining events. So the first one we're going to talk about is this. If A and B are events, then A union B is a new event. It's the event where A occurs or B occurs. Now here's a very important remark. When I say that A occurs or B occurs, that or includes the possibility that both occur, right? If both occur, that still falls under the category of A occurs or B occurs. Because the or is, you might have heard this word, is inclusive, right? It includes even the possibility where both occur. We'll talk more about this when we learn about logic. So here's an example. Suppose we toss a coin 4 times in a row. So let's first think about what our sample space looks like. How many elements there are in the sample space, what those elements look like. Right, so tossing a coin 4 times, each time we toss the coin, we have either heads or tails. That's really all we know. And this question that it doesn't specify, but you can assume this is a fair coin. Okay, so here is an illustration of the sample space S. We'll call it S. Right, so the first thing here, top left, this is where they're all heads. The next one is where the first one is head, second is tail, and the next 2 are heads, and so on. Okay, so if you try to list them out yourself, you should be able to see that there are 16 possibilities. So there are 16 elements of S, and these are they in the table. So that's okay. So that's our sample space. Now let's talk about some events in this sample that are subsets of the sample space. So let A be the event where the first 2 tosses are heads. Okay. So you see here in the diagram that part of it has been circled, and that's A. So it's a subset of S, and it's the event where the first 2 tosses are heads. Notice that, for example, here the first toss is a head, but not the first 2 tosses. So this event A includes all the cases, all the outcomes where the first 2 tosses are heads, and no other, right? It includes those outcomes and no other outcomes. Okay, so that's one event A. Now let's introduce a second event into the picture. Let B be the event where there are exactly 3 heads. So if we take a look here, the area that's circled by B is the place where there are exactly 3 heads. Right? This has exactly 3 heads, exactly 3 heads, exactly 3 heads, and exactly 3 heads. Now, very important, notice it is possible for something to fall into both A and B. Right? It's so like this here, HHHT, the first 2 are heads, and exactly 3 of the 4 are heads. So this falls into both A and B, right? It's part of both A and B. It's an element of both A and B. And similarly for head, head, tail, head. Now, A union B is the event where the first 2 tosses are heads, or there are exactly 3 heads. So you see that A union B simply encompasses everything of A and B. And it also includes the overlap, right? So very important, it includes the overlap. That goes to the point earlier that when I say A occurs or B occurs, that includes the possibility that both occur, right? So A union B, which represents this idea of A or B, this includes the possibility that A and B are both true, right? So in other words, something like HHHT falls into both A and B, and it is included in A union B. So not just things over here that are just part of B, and not just something like here at the bottom, which is just part of A, but it also includes the overlap. Okay, this may be obvious to folks, but I just need to make sure this is clear. This is a really important point. Okay, so that's the event A union B. It's a new event, right? It's not the same thing as A. It's not the same thing as B. It's something new. It's a new subset of the sample space. Now, for this particular example, what would the probability of A union B be? Okay, so the probability of A union B, that would be the cardinality of A union B divided by the cardinality of S. I should point out all the outcomes in the sample space are equally likely to occur because it's a fair coin. Anyways, if we count them up, it's 6 divided by 16 or 37.5%. So this was one way of combining events using union, A union B. And now another way to combine events is if A and B are events, then A intersected with B is the event representing A and B occur, right? They both occur. So not just one, not just A, not just B, but both of them occur at the same time. So that's what A intersected with B is. It's a new event, it's a subset of S, it's a subset of the sample space, but it's a new event. So same example, suppose we toss a coin 4 times in a row. Again, this is our sample space. Let A be the event where the first 2 tosses are heads as before. Let B be the event where there are exactly 3 heads as before. Now we're going to talk about what is A intersected with B. That's a new event. So that's going to be the places where there are the first 2 tosses are heads and there are exactly 3 heads, right? So for example, something like THHH, that's not going to be part of the intersection because the first 2 tosses aren't heads. Something like HHTT is also not going to be part of the intersection because it doesn't have exactly 3 heads. The part that is going to be in the intersection is the overlap, right? So this is A intersected with B. So A intersected with B is the event where the first 2 tosses are heads and there are exactly 3 heads. And now we can think about what is the probability of A intersected with B. So in other words, what's the probability that the first 2 tosses are heads and there are exactly 3 heads? So that would be probability of A intersected with B, which is equal to the cardinality of A intersected with B divided by the cardinality of S, which is 2 divided by 16, or 12.5%. Okay, now one more way of not really combining events. It's not really combining events, I guess. It's more a way of producing a new event from an old event. So if we consider a sample space S to be our universe, and let's say we have an event A. So A is a subset of S. That's our event A. A is our event. It's a subset of S. Then the complement of A is the event representing A does not occur. A does not occur. So A means whatever, something happens, whatever it is. And the complement of A is everything outside of A, meaning all other possibilities, meaning where A does not occur. So same example, suppose we toss a coin 4 times in a row. So we have this sample space. Let A be the event where the first 2 tosses are heads. Now we want to consider what are we going to have for the complement of A. So the complement of A is the event where it is not the case that the first 2 tosses are heads. Okay, it is not the case that the first 2 tosses are heads. Okay, wrap your head around that. What does it mean to say that it is not the case that the first 2 tosses are heads? What it means is that it's possible that one of the first 2 tosses are heads, right? It's possible the first toss is a head, it's possible the second toss is a head, but it is not the case that that both of the first 2 tosses are heads, right? So like something like here is head, tail, so the first toss is a head. However, this is part of A complement, right? Because it is not the case that the first 2 tosses are heads. Anyways, this gray area is the complement of A. And what is the probability of the complement of A? So as usual, it's the cardinality of the complement of A divided by the cardinality of S, which is 12 divided by 16, or 75%. Okay, now here's a new concept that we're going to use very shortly, the idea of mutually exclusive events. So this is really just a formal way of saying an idea that we've had before, the idea of no overlap. Okay, so mutually exclusive means no overlap. So let's say we have 2 events, A and B, in a sample space S, right? So 2 events, A and B, in a sample space S are mutually exclusive if their intersection, right, A intersected with B, is the empty set, right? So here's an example, a very, very generic example. We have a sample space S, and you have a an event A and event B, notice there's no overlap at all between them. In other words, their intersection is the empty set. There is nothing in their intersection because they don't intersect. So we say that events A and B in this case are mutually exclusive. In other words, what it means is that when I say that A and B are mutually exclusive, what we mean is that if something is in A, then it's definitely not in B. And if something is in B, then it's definitely not in A. There's no overlap between those two events. Okay, so now what we want to do is try to find a formula, a general formula for the probability of A union B. Right? We saw an example a short while ago of probability of A union B, but in that case, we were just able to, we were able to actually count out the outcomes and find our answer. But can we come up with a general formula for probability of A union B? So here we're going to come up with the formula ourselves. So probability of A union B. Well, now here in this work that I'm going to do here, I'm going to assume that all outcomes are equally likely to occur. Now, in general, that's not always going to be the case, right? In a general experiment, some outcomes may be more likely than others. However, this formula actually works even in those cases, right? Even in cases where outcomes are not equally likely to occur. But the math is more tricky then. So the sort of the proof for the formula that I'm going to show you now is going to rely on the assumption that all outcomes are equally likely to occur. But again, this formula will work even when it's not the case that all outcomes are equally likely to occur. Okay, so probability of A union B. So again, we're assuming all outcomes are equally likely to occur. So this is just the cardinality of A union B divided by the cardinality of S. This is our very basic probability formula that we had from the beginning. Right, again, this is our event is A union B, so it's the cardinality of the event divided by the cardinality of the sample space. Now, what's the cardinality of A union B? Well, we have the inclusion-exclusion formula from our discussion of counting. So this is the cardinality of A plus the cardinality of B minus the cardinality of A intersected with B, all divided by the cardinality of S. Now, next, we can break up this fraction like this. And now, if we take a look here, this first term is really just the probability of A. The second term is just the probability of B. And the third term is just the probability of A intersected with B. So here we have our formula. The probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersected with B. Now, of course, we still have to figure out what these three things are. But in many examples, it is relatively easy to figure out what these three things are, and it is difficult to figure out directly what this is. So this formula is very handy, right? So again, if I can figure out directly what probability of A union B is, I can count them directly, but I do have an easy time with these three, then I can use this formula. So now here's something to consider. Now that we have this idea of mutual exclusivity, so if A and B are mutually exclusive, then we know that, well, A intersected with B is the empty set. So the probability of A intersected with B is 0, right? Because A intersected with B means that A occurs and B occurs. But if A and B are mutually exclusive, then meaning there's no overlap, well, then that means that if A occurs, B does not occur. And if B occurs, then A does not occur. So again, if A and B are mutually exclusive, then the probability of A intersected with B has to be 0. And therefore, if A and B are mutually exclusive, we can simplify this formula. Our probability of A union B, we found it's probability of A plus probability of B minus probability of A intersected with B. But we can simplify it because in this case, probability of A intersected with B is 0. So we are left with that the probability of A union B is just probability of A plus the probability of B, and that's it. It's pretty simple. But again, this is only in the case where A and B are mutually exclusive. If they're not mutually exclusive, then we have to use the longer version of the formula. Okay, so now let's use this this formula, or really these formulas, right? Because there are kind of two formulas here, closely related ones. Let's use them in some examples. So two cards are dealt from a shuffled standard deck, and the order is insignificant. Okay, so it's just a group of cards. I'm not lining them up in an order. I just grabbing two cards. I don't care about the order. What's the probability that both are red or both are clubs? Okay, both are red or both are clubs. So first thing that's often helpful to do is to figure out what the sample space is. The sample space S is the set of all two-element subsets of the deck, right? In other words, all possible groups of two cards that you could make from the deck. What is the cardinality of S? Well, there are 52 cards in the deck, and we're taking a subset of two, a two-element subset. We're just taking a group of two cards, and order doesn't matter. So the cardinality of S is 52, choose 2. Next, let A, which is a subset of S, be the event where both cards are red. What's the cardinality of A? Well, there are 26 red cards, so cardinality of A is 26, choose 2. And again, A is a subset of S, so we're talking about groups of two cards. So that's why it's choose 2, 26, choose 2. Let B, which is also a subset of S, be the event where both cards are clubs. And the cardinality of B is 13, choose 2, because there are 13 clubs, and we're choosing 2 of them. Now, A and B are mutually exclusive events. Why is that? Because all clubs are black, right? So if a card is red, it's not a club. Or more specifically, if we have a group of two cards that are red, right, then they cannot be clubs because clubs are black, and vice versa. If we have a group of two cards that are clubs, they cannot be red because clubs are black. Okay, so A and B are mutually exclusive events. Now, notice, let E be a subset of S, which is a subset of S, be the event where both cards are red or both cards are clubs. This is really what we want, right? We want to know what is the probability of E, right? What's the probability that both cards are red or both cards are clubs? Now notice that E is equal to A union B. Okay, that's why we set up A and B, because we're going to now be able to use A and B, the union of A and B, to represent E. Well, A union B we see is equal to E, right? The probability of E is what we actually want. E is the event where both cards are red or both cards are clubs. But it's easier to deal with when we can represent it as A union B. Okay, now we can use the formula, and we can use the simpler version of the formula because A and B are mutually exclusive events, right? So probability of E, which is equal to probability of A union B. Again, mutually exclusive events, so this is equal to probability of A plus probability of B. We don't have to worry about subtracting anything in this example. Probability of A is cardinality of A divided by cardinality of S, and probability of B is similar, cardinality of B divided by the cardinality of S. And we have all these things figured out already. So it's this, and when we simplify it, we get this, which is approximately 30%. Okay, so if we take two cards from a deck, the probability that both are red or both are clubs is a little over 30%. Another example, very similar. Two cards are dealt from a shuffled standard deck. Again, order is insignificant. What's the probability that both are red or both are face cards? Face card is, again, remember, Jack, Queen, King. Those are the face cards. Now here, if you think about it, you may realize that this, the only real significant difference between this question and the earlier question is that there is overlap, right? In other words, it's possible to have two cards that are red and that are also face cards, right? In the earlier example, that wasn't possible, right? Because if both cards are red, then you cannot have both of them be clubs. Okay, but here we could have overlap, so we'll have to keep that in mind. So again, going through the steps. The sample space S is a set of all 2-element subsets of the deck. The cardinality of S is 52 choose 2. Let A, which is a subset of S, be the event where both cards are red. Cardinality of A is 26 choose 2. Now let B, which is a subset of S, be the event where both cards are face cards, right? Similar to what we did before. Now, what is the cardinality of B? Well, we just have to know how many face cards are there. Well, keep in mind that there are 4 suits in a deck, and each suit has 3 face cards. So that gives us 12 face cards, and we need to choose 2 of them. So cardinality of B is 12 choose 2. Now note that A and B are not mutually exclusive events, right? Because it's possible to have, or there are many different ways, in fact, for us to have a group of 2 cards that are both red and both face cards, right? So there is overlap among A and B, between A and B. Okay, so now we are going in the course of the work to solve the problem, we're going to need to deal with the intersection because of the formula that we're going to use in a minute. We need to figure out what is the intersection of A and B. The intersection of A and B is the event where both cards are red face cards, right? It's a subset of S, so you have 2 cards, and they're both red and they're both face cards. So they're both red face cards. Now we can ask, what is the cardinality of A intersected with B? Well, how many red face cards do we start off with? 6. Okay, if you look at the diagram, the chart of deck of cards, you'll see, or if you think about it a little bit, there are 3 face cards of hearts and 3 face cards of diamonds. Those are red. The other face cards are black. So there are 6 red face cards. So cardinality of A intersected with B is 6 choose 2. Okay, now we have all the pieces we need to solve the problem. Well, actually, hold on just a second. Let E, which is a subset of S, be the event where both cards are red or both cards are face cards. No. Yes, or both cards are face cards. Yes. In other words, E is A union B. E is A union B. So now we can figure out probability of E. Probability of E is equal to probability of A union B, which is, according to our formula, probability of A plus probability of B minus probability of A intersected with B. So now this is, cardinality of A divided by cardinality of S, and that's for probability of A, and then we add probability of B, and then we subtract probability of A intersected with B. We have all these numbers already, we just need to plug them in, and we get approximately 28%. Okay, one more formula and one example for it. So how about formula for probability of the complement of A, right? Now you might be wondering, hold on, we seem to skip the formula for intersection, right? We did the formula for union, now we're doing the formula for complement. What about the formula for intersection? Next video. Okay, so probability of a complement. So we're again going to use the things we already know to figure out this formula. So probability of a complement. So again, I'm assuming that all events are equally likely, even though that's not always going to be the case. However, similar to before, this formula will work. The formula that we're going to come up with will work in all cases, no matter if all outcomes are equally likely or not. However, for this work that I'm doing to find the formula, I I don't want to show you the more complicated version. So for this simpler version, I'm assuming that all events are all outcomes are equally likely. Okay, so if all outcomes are equally likely, we can use our standard formula for probability, right? Standard probability formula. So in other words, it's the cardinality of the event divided by the cardinality of the sample space. Okay, so now A complement is S minus A, right? S is our universe. It's S minus A. Okay. And so we have the cardinality of S minus A divided by the cardinality of S, which we have a formula from counting, our discussion of counting, that tells us that this is the cardinality of S, right? The cardinality of the universe minus the cardinality of A, all divided by the cardinality of S. And we can break up this fraction. And this is, so the cardinality of S divided by cardinality of S is just 1. And then the second thing is just probability of A. So we have 1 minus probability of A. So this gives us a formula for the probability of A complement. Again, probability of A complement is 1 minus probability of A. Okay, now there's a nice corollary to this formula, meaning a corollary is like a result that comes, a secondhand result, right? In other words, we have this formula, but as a result of having this formula, we can come up with another formula. So here it is. So we know from this formula that probability of A complement is equal to 1 minus probability of A. Now we can subtract 1 from both sides, giving us this. Now we can negate both sides, right? We can do negative on both sides. So that gives us this. And then when we simplify, we get this. And so what this means is we have here a new formula for probability of A. Thus, probability of A is equal to 1 minus probability of A complement. Okay, so that's a sometimes nice little formula. So it's, notice probability of A complement is 1 minus probability of A. Probability of A is 1 minus probability of A complement. All right, now let's use this formula on the left that we found, that we came up with for probability of A complement. Let's use it in an example. So similar example to before, 2 cards are dealt from a shuffled standard deck where the order is insignificant. What's the probability that they are not both red? Okay, not both red. Okay, so this is, you have to wrap your head around this. Not both red. Could be one of them is red. Okay, but not both of them are red. Not both red. That is, what's the probability that at least one is black? Maybe one of them is red. That's fine. But we want to know what's the probability that they're not both red. Okay, that at least, meaning what's the probability that at least one is black? Okay, so the sample space S, as before, is the set of all 2-element subsets of the deck. And as before, cardinality of S is 52 choose 2. Now, what's our event A? So let A, which is a subset of S, be the event where both cards are red. Okay, now this is the opposite of what we're trying to find the probability of. Okay. So again, A is the event where both cards are red, both are red. Cardinality of A is 26 choose 2 because there are 26 red cards and we need to choose 2 of them and the order doesn't matter. Now, the complement of A is the event where not both cards are red, right? In other words, A is the event where both cards are red. The complement of A is everything else, meaning where not both cards are red. Maybe one card is red, but not both are red. And that's what we want to find. We want to find the probability of A complement. So probability of A complement is equal to, according to our formula 1 minus probability of A, which is 1 minus the cardinality of A divided by cardinality of S, which is this, which is approximately 75%. So that's pretty interesting. So if we take 2 cards, there's about a 75% probability that they're not both red, meaning that at least one of them is black. All right. Now, the book there are actually at least two other ways to solve this problem. One of them is using the corollary from a few minutes ago, and the other way is actually using union. So you can actually solve this problem using probability A union B. So both of those ways of solving this problem are found in the book, and you can read them if you're interested. This is a general thing you'll see a lot in counting and probability, is that there are often a few different ways of solving a problem. But just to be clear, you don't have to use those other ways if you don't want to. If you want to see alternative ways, then look in the book. But if you answer like this is a perfectly good answer. And those alternative ways lead to the same result anyways, right? Okay.